The next summation that we're going to do is not I, but I squared. So the index starts with 1. We're going to go to this arbitrary number n, but we're going to add up things. So it's 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared all the way to n squared. So let's try what Gauss did, the n's, and see if that matches. Well, 1 plus 36 is 37. 25 plus 4 is 29. 9 plus 16 is 25. So not the same number, not the same method is going to work. But let's organize things in a table. So using what we know, when the index is 1, we got 1. When the index was 2, 1 plus 4 would be 5. When the index was 3, 1 plus 4 plus 9 would be 14. When the index is 4, we would go down, so on and so forth. So if we look at that 1, 5, 14, 30, 55, 91 to an index of 6, they're not increasing at the same rate. So let's look at what they are increasing by. Well, it's changing by 4 in the first set, 9 by the second set, 16 by the third, 25. And those numbers look very familiar. They look like they're increasing by a pattern, but not consistently. So if I look at the differences of those, it'd be a difference of 5, of 7, of 9, 11. And then I finally see the third time I look at the changes, I'm looking at a change of 2 every single time. So I want you to think about, if we found the change of our numbers was constant right here, what kind of function would that be? It went up by 1, and then it went to 5, and then it went to 9, and then it went to 13. So we're increasing by 4 every time. That function, if you were to graph it, would just be a line. So it doesn't really matter where it starts, it's a line. Okay? And the slope of that line would have been our changes. So looking at that as a derivative, the change, because subtract them, change per 1 would be 4 every time, the way I constructed it. 1, 5, 9, 13. But that's not what's happening. If I look at this change, so the change of the change, I'm looking at 5, 7, 9, 11. So if the change of the change were constant, that would be a quadratic function. Think about the second derivative of a quadratic. You would be getting down to a constant when you look at it the second time. But it doesn't have the change constant there either. It has the change constant when we do it the third time, looking at the changes of the changes of the changes. So it's like a third derivative down. That's the slope, and it's finally constant after you do it 3 times. So this is a cubic function. What we are describing right here, this pattern, is cubic. So because this is cubic, let's think of the general form of a cubic equation. Well, it's for sure going to have a cubed, and then a constant in front of it, and then a squared component, and then a constant in front of it, a linear part, and then a constant in front of it, and then a constant part. So what are we trying to find? We're not trying to find the sum of I, but we're trying to find the sum of I squared and what that equals. So what we really need to find is this equation right here, because all those numbers that we're putting together up here, in this table, all of these are going to be put together, and it's going to be a cubic function in terms of n. So our job is to find what these mystery coefficients are, a, b, c, and d. So that's what we need to find. So how do we do that? Essentially, we're going to solve a system of equations by doing a matrix, and then we're going to use the RRF feature, reduced echelon form. So we have a bunch of n's. We have a n to the third plus b n to the n squared plus c n plus d. And we know what those are going to equal. we know that that stuff, that cubic stuff, is going to equal our sum to whatever n is. So let's start simple. Let's say n is 1. So we're going from an index of 1 to 1. The start index, the lower bound is 1, the upper bound is 1. If we put that in, we know what that's going to equal. It's going to equal 1 because 1 squared is 1. So what was n? It was 1. So remember, this is a n cubed, b n squared, c n plus d. Well, 1 cubed is 1. 1 squared is 1. 1 is 1, and the constant doesn't change. And we know what that's going to equal, 1, I squared. Now we're going to do it again. Let's say it's the sum from I equals 1 to 2. Well, we know what that's going to equal, 1 plus 2 squared. So that would be 5. And n was 2. So now n cubed is 8 a's. N squared is 4 b's. N was 2, which is c, and I still have a constant d. So I'm doing this 4 times because when you solve a system of equations, you need the number of equations to equal the number of variables. Because what we're essentially going to do is we're going to first solve for d in terms of a, b, and c. Then we're going to solve for c in terms of a and b, and we're going to put what we just found for this answer in for d. And then we're going to solve for b in terms of a, because whatever we solve for c is going to go in there. Whatever we solve for d up here is going to go in there. And then we're going to do it one more time. We're going to solve for things in terms of a, because what we solve for b is going to go in there. It's going to be a bunch of a terms now. C is going to go in there, a bunch of a terms now. And d is going to go in there, a bunch of a terms now. So then we can find what a is, and then we can find what b is, and then we can find what c is, and then we can finally plug all those numbers in to find what d is. So it's a long process. To cut that short, you can see that n to the third, n when it equals 3, cube that, n when it equals 4, cube that, and then square it, take it, and leave the constant. So we're doing it 4 times because we want to have 4 variables to solve for. Did we have to choose n equals 1? Nope. We could have chose to start with n equals 5. And then we could do n equals 6, n equals 8, n equals 9. It's just much easier to use smaller numbers. So n equals 1 is a great one to start with. To do the manual method of solving equations, essentially what we're doing is we're going to subtract things away. I described the longer process up there, but the shortcut method is to stack them all up and subtract the ones above it from below it. So a, take 8a minus 1a, you get 7a. 27a minus 8a, you get 19a. 64a minus 27a, 37a. And you do the same thing with the b's. 4b, take away 1b, 3b. 9b, take away 4b, 5b. 16b, take away 9b, 7b. And then you finally get down to a 1 constant c. Do that the next step down. 19a minus 7a, 12. 37a minus 19, 8a. 5b minus 3b, 2b. 7b minus 5b, 2b. And then the constants, subtract them, go away. And you're doing that over here too. 9 minus 4 is 5. 16 minus 9 is 7. Do it one more time, and you get out 6a. That goes away. And 2, which means a is 1/3. And now we can work our way back into whatever equation we want. I like this one because it's simpler. It starts with a 12. So I'm going to put my 1/3 in for a. And now I can solve for b. And now I'm going to go up to the next one. I like the top one because it's simpler. I know what a is. I know what b is. I can solve for c. And now I know what c is, and I can put it into the simplest one I know, which is the way top one, where they're just plain, where n equals 1, and that solves d to be 0. So a times n to the third, a was 1/3, 1/3. B was half, so n squared times 1/2. N was with C, and C is 1/6, 1/6. And D is 0, so I don't need to write it. So what does that equal? That was the sum of I squared with an index starting at 1 and going to n. So this equals this. And I can reformat that a couple different ways. I found a common denominator of 6, so times that by 3, you get 3n squared. Times that by 2, you get 2n cubed. And then you can factor out an n, and then you can factor out an n plus 1. So this general form here looks very similar to what we had for the summation of I. The summation of I, if you recall, was n times n plus 1 over 2. And now this is the same start with a 2n plus 1 over 6. Whew. Another way you could do that is with matrices. It has the same start where you have to find what your four equations are, which we did up here with n equals 1, n equals 2, n equals 3, and n equals 4. But you can let the calculator do all that work for you in the sense that take the coefficients. Here is what all those are going to be multiplied by. So A is going to get multiplied by those pieces. B is going to be multiplied by those pieces. C by those. D by those. And that's going to equal the things on the end, 1, 5, 14, and 30. So these variable terms are being multiplied by our A matrix. But I really want this. So in order to get rid of that, I should multiply by the inverse to both sides. So X, this matrix, is equal to A inverse matrix times B. And if you do that with an RREF in your calculator, you get out your original. Sorry about that. So once you have these typed into matrix A and matrix B in your calculator, you're simply multiplying A inverse by B. And you're doing that all by getting the matrices from your matrix function right there when you do second. So that gives you a single matrices with a bunch of ones going down the diagonal, and then you can see all the decimals, which you can convert to fractions if you go math frac. And the last way you could do it is you could do one single matrix, which is a combo of that first one, A and B, in a 4 by 5 matrix. So do that and then go into the matrix option, the math, and RRF of that single matrix. And then you get out a matrix that looks something very similar to it. And again, you can do math frac to do that. So 3 different ways to do it. You will not have to do this again. We're just learning and investigating right now. So 3 ways, and you're always coming out with the A value as 1/3, the B value as 1/2, the C value as 1/6, and the D value as 0. And that gives you this formula right here. So now we know the sum of I squared and what that equals, and we know the sum of I, what that equals. And these are closed forms. There's no dot, dot, dot. These are closed forms. So write that one in your notebook. And then are you ready to do it for I cubed? It goes much faster for I cubed because we know some tricks. So if we look at I cubed and kind of set up a similar table of values, when I is 1, I cubed is 1. When we look at I is 2, 2 cubed is 9. Well, I should say 1 plus 8, which is 9. 3, index of 3 would be 1 cubed plus 2 cubed plus 3 cubed. So 3 cubed, which is 27, plus that one, which is 9, gives you 36, so on and so forth. And what you're actually seeing is, if you look at these, it's like 1 squared, that's like 3 squared, that's like 6, that's like 10, that's like 15. And that pattern, we've already seen that pattern before. That pattern showed up with I, the sum of I. Remember that pattern? When n was 1, the sum was 1. N was 2, sum was 3. N was 3, sum was 6. So you see that? 1, 3, 6, 1, 3, 6, but they're squared here. So really easy. take the summation of I, which was this, but it's squared. Done. Much faster. You should write that one in your notebooks too.